Let's solve some circuits here. A little light would be helpful. There we go. Okay. So for solving circuits, we've got three kind of main laws that we need to remember for sure. And maybe there's some more also, but we'll start with Ohm's law. Ohm's law is just V equals IR. We need it quite often to go between those when we have resistor circuits anyway. Kind of the dual of that when we're doing capacitor circuits, we're going to do Q equals VC, or V equals Q over C might be helpful. So relating the charge and the voltage, or the current and the voltage. Kirchhoff's voltage law, KVL, we just want to say the sum of the voltages around the loop equals 0. So we'll think about walking around the loop. Technically, when we walk around the loop and we have negative sign, we'll make a negative in the equation, negative ES, whatever, looking at the signs we come to. And technically, though, we're actually adding up the negative of the voltage rises, but all of them have negative signs on them, so it's the same equation. So it's just easier to think of walking around the loop to do the KVL. So sum of the voltages around a loop, you go uphill, across country, uphill, come back down, you come to the same height. You have no change in elevation. So the potential difference, remember voltage is potential difference, the difference when we go around the loop is 0. Okay. KCL is just in equals out. Just remember the current in, C is the current, so the current in equals current out. So if we have a node like this, has certain current going in, others going out, what comes in has to go out. So you add up all the ins, add up all the outs, and they should equal each other. Okay, Ohm's law, KVL, KCL. So first off, we need to have, so these equations, notice, have V's and I's in them. We need to have some V's and I's to write equations with. So we need to name them and label them on the circuit. So when we name a voltage, we give it a name, a letter, a variable, and then we put plus and minus so we know where is the high potential, where is the low potential, where does it go from low to high, or whatever. What is the difference? For currents, we need to put a variable and put an arrow, right? So say what direction are the positive charges moving. Remember, current is positive charge, even though we know actually it's electrons go in the opposite direction, but we do things with positive sign convention. All right, and one more rule is if we want to use with no negative signs in it, we have to make the resistors, right? Ohm's law, is for resistors. We have to make the resistors such that the flowing current comes into the positive. So, for example, let's go ahead and name a voltage for this 2 ohm resistor. Let's take a step back. So we know voltage sources are what pushes energy into the circuit. And so positive for a source, kind of think of the positive as where we're going to check what the current is doing, right? Or what the energy is doing. So a source will have a positive current coming out of its positive terminal, positive side, right? And so plus this current is positive for the source current because it's coming out. And so if I would calculate the power PIV or what have you for the source, it would be positive produced power, right? It's the so sources, we wouldn't do Ohm's law for a source because it's not a resistor, right? So it has no R. We wouldn't do Ohm's law for a capacitor either because it's not a resistor, right? Ohm's law is just for resistors. Here's a resistor. All right, so now we've defined that the source current was coming out, so we'd expect the resistor current to be going from left to right. And when we have a branch of things, notice these three are in series, right? Current coming through this 1 ohm resistor has no choice at all. There's no way for it to escape. It all has to go through the source. Similarly, current coming from the source has no choice, no escape routes. It all has to go through this 2 ohm resistor. All right, and so these three things are in series. And so in general, even though we could say the current in the source, name it, we could give current to this resistor, name it, to this resistor, name it, but they're all the same current, right? So at this node, we would say the current in is the 1 ohm resistor's current, the current out is the source current, so in equals out, this current equals that current, this current equals that current. So it's kind of pointless to write those simple little equations. So when you're giving names to all your V's and I's, just name one per branch would be the easiest. And it's good to start with the sources so you get everything kind of in the positive direction, in the direction we think they're going to be positive when we calculate the numbers. But the only, as long as you write your equations with respect to the things you define, you're all good. You might come up with an answer that gives us a negative voltage or a negative current. That just means we guessed wrong and the actual one is in the opposite polarity, but that's fine. We still know which way it goes. Okay, so we'll start with the source. Current comes out, and so for this resistor, then we should name its voltage plus here and minus there, because we want, for resistors, positive is coming into the plus, because resistors use up energy, right? They take in energy. It's like capacitors, inductors, everything but sources basically will use up energy. We call them loads, right? They're a load on the system, something the system has to carry, something the system has to feed, right? So for the positive sign convention for a resistor, for Ohm's law to be V equals IR, not V equals negative IR, we want the I to come into the plus side, right? So how about this resistor down here? Which direction, where would it, which side would be the plus on it? Well, we can kind of think of backing up this current. If we drew which direction it was flowing down here, it's going into this side, so this side has to be the plus. This side has to be the minus because it comes out and continues on around, right? All right, so similarly, if we have current coming in here, there are no sources here, so we just kind of expect it to split up and go on through. Actually, I want to probably put these over here on the other side just to have more room for all my labels. So let's say this current comes down here and this current goes this way. All right, and let's just call this I3 and call this one I4 just because it's the I and the 3 ohm resistor, I and the 4 ohm resistor. Okay, so we've named our currents, and again, I don't need one down here because this one comes on around, comes back, so this one also has I4 in it, all right? Voltage-wise, again, we've made the current coming down, so the top side is the plus of this resistor, the left side is the plus of this resistor. How about the 5 ohm resistor? Current's coming this way, right? All the I4 is all going this way, so it's going to come into the right-hand side of this resistor, go out this side. All right, so we got our voltage polarities. So we could name them. I guess we'll go ahead and name them. So we'll call this one V2, but I want to get a little more specific, a little easier when I'm writing equations and use Ohm's law. Ohm's law says what? It says VER, right? V equals IR. So really, we could say, we could name this I2, or we could name it, the current in this resistor is IS, so we could name it 2IS. So that's really RI, but anyway, I guess I'll put the minus down here a little bit further so we can see. All right, so this is V2, or I could just call it 2IS because IR, IS times R, right? So similarly, this one we could call it V1, but it's also 1IS. Right, RI, IR. Okay, we could say IS times 1, but it's a little awkward that way. All right, how about the resistor in the middle? We can name its voltage V3, but what is V3 equal to? 3I3, IR. I3 times 3, so 3I3 is also this voltage. All right, so it's a voltage because it's R times I, so still in volts. Don't ever just name it, don't ever call this voltage 3 or call it I. We got to keep track. We've got 3 different variables at least on this picture. So if you're adding up voltages in KVL, make sure you only add voltages, right? 3I3 is a voltage now. I'll add it as V3 or add it as 3I3. All right, similarly here, we could name this one V4. Ohm's law would say that's 4I4. All right, VER. And down here, we can name this one V5. And its Ohm's law name would be IR. Its I is I4 and its R is 5. So we say 5I4. Okay. So we kind of got everything defined and maybe did a little bit extra by putting in the Ohm's law names in there. So I would say we are good with A. Oh, and we are good with B. I already did applying the Ohm's law part too. Okay. Find R total. All right, so now we're going to take a step back. And so there are 2 kind of ways to solve a circuit. One way is doing a lot of resistor combinations. So if we have simple circuits like this that have only one source and a whole bunch of resistors, we can combine the resistors into one and do some good math that way. Some circuits, if they have multiple sources, you might not even be able to combine the resistances. And so then we'll rely heavily on writing sets of equations, KVL and KCL equations, and then solving it with a lot of algebra. Okay. Either way, there's a lot of algebra actually, but solving it with equations that we've written out. So let's do it the first way with equivalent resistance way first. So let's find R total. So we're gonna, when we find R total, then we will have just a little basic circuit like this, right? We'll have R total will be the resistance that models all those guys put together. We'll have our source voltage, something is still here, and we'll still have the same current. So the source won't know if there are 5 or however many resistors there are, or if there's just one, right? It'll the VS, IS, everything will be the same as far as the source is concerned. So we still have that same IS there. So let's look at R total. What do we have here? So can we see that these two resistors, the 4 ohm and the 5 ohm, are in series with each other? Okay, hopefully that kind of makes sense, because we've got current flowing through the 4 ohm. It has no way to escape anywhere. It all has to go through. Just like we said, that's why I4 is here. So if they have the same current in them, they're in series, right? And so we could combine this branch to just be a 9 ohm resistor, right? Because R is in series. I don't really want to write an equation there, but resistors in series just add up, right? R series is R1 plus R2 plus R3. They just add. So we would have equivalent resistance here of just 9 ohms. So if this became just one resistance, I'll make a mess out of my picture. I probably don't want to. Anyway, this became one resistor. It'd just be one resistor, 9 ohms. Now that resistor is in parallel with the 3 ohms, right? Because they both touch this point and they both touch this point. So then we have 3 ohms in parallel with 9 ohms. If that becomes one resistor, I mean just one thing here, so then my eraser became that one equivalent resistor. So now the source is in series with this resistor, in series with this equivalent resistor, in series with the 1 ohm resistor, right? So now we can just add them up, because resistors in series just add up, and so we can get the total resistance that way. And so we could say, so I highly encourage you to draw lots of pictures. Don't conserve paper like I'm trying to do, and just do it as long and continue to see it. So, but what I'm going to write here then will be R total will be 2 ohms. So starting out from the source side, we're going to have 2 ohms, and that's going to be in series with this big combination, which is what? This combination is 3 ohms in parallel with 4 ohms plus 5 ohms, right? Because those are in series. So parallel is this, series is pluses, right? So we've got the 3 ohm in parallel with that, and then when that becomes 1, that is in series with the 1 ohm. So I'm going to add 1 ohm onto there. Okay? So that would be my equation for R total. Well, a kind of a symbolic equation. So doing it purely with math, then we got to get this parallel thing working. So we can do 1 over 3 plus 1 over 4 plus 5 down here, because that's how we combine in series. And that then gets added, 1 added to it. All right, so what is R total? We got 2 plus 1 divided by, get a parentheses in there, 1 divided by 3 plus 1 divided by 9. Close those parentheses. And then add that 1 on the end. And just double check that your calculator is interpreting things right, but that looks good. So 21/4. Excuse me. 5.25 ohms is R total. Alright, so that's part C. Part D says find IS, V1, and V2. Alright, so IS is on this in this little circuit, so whatever we can find in this little circuit, let's use it before we have to go back to the big circuit to find things there. So V1 and V2, you can't see them here, they're inside this R total, so we'd have to go back to the big circuit to figure out what they are. But let's get IS first. So how can we get IS? Well, IS is the current out of the source, but it's also the current into R total, right? And the voltage is plus all up here and minus all here, so VS is the voltage across R total, right? And so Ohm's law says, we got Ver, in this case VS is the voltage across this resistor. IS is the current in this resistor. So Vs equals IS R total. So IS equals Vs divided by divided by R total. And we need a number for Vs. Let's just say Vs equals 12 volts. Make it readable. All right, so IS is 12 over 5.25. 12 volts over 5.25 ohms. So IS equals 2.286 amps. 2.29 amps. We'll leave it with 4 sig figs for a minute because we might use it for other things. All right, IS. Let me get a drink here. Sheesh. Okay, and so V1. So where's V1? V1 is the voltage across this 1 ohm resistor. So we can't see it here. We'll come here. But what do we know about V1? Can we use VER? All right, or do we have to use KVL and KCL? But luckily we can use VER. If we do VER for this 1 ohm resistor, we're looking for V1, and it's the voltage across this resistor. And we know R is 1 for this resistor. And what is the current in this resistor? Remember, IS is a current on this whole branch. So this is just IS, which we know. So we can just say that V1 is IS, which we just got, 2.286 amps, times R, which is 1 ohm. So that would pretty much be 2.29 volts is V1. All right, or 2.286, but okay, good. And similarly, we could do a similar thing for V2, right? Because IS is a current in V2, so V2, one way to do it is V2 is IS times R. I guess we'll just put some R2, right, which is 2.286 times 2, whatever, times 2, 4.57 volts is V2, right? Probably the easy way, but let's try one other way. We can do it a different way with, no, we can't. Never mind. With KVL, but we don't know that we'd have to calculate this equivalent resistance, and then we can do KVL around the loop and figure out each individual voltages. No, we would know. This is a good way to do it. Okay, but KVL could give us more information, but it would be some more steps. So let's just leave it at that. All right, so that's kind of one way to do it. If we wanted to get things over here, like I was saying, now we could get V3 with KVL. So we would have to do V1 and V2 this way, but if we write KVL around this loop, we could say, let's just put a little note in here and we'll do it again in a minute. Let's go around this loop. So we have negative Vs. So remember, start somewhere, walk around. So we hit the minus sign first, so it's negative Vs. We get to V2, it's plus V2. Keep on walking around. We hit V3, but we come in the plus side of V3, so it's plus V3. Continue on around. We hit the plus side of V1. So all these guys are plus V1. Coming around. We get to where we started, so we say equals 0. And this is hopefully pretty obvious. So it's saying the source voltage is equal to the other 3 voltages add up. And the source is what's causing all the voltage. If there was no source, there's no voltage. Nothing happens, right? So if we go up this way to this point, we go up 12 volts. If we go this way, we go up 2.29, then we go up some number for V3, and then we go up the 4.57, and we get up to here. And so we could get V3 now from this, since we know Vs, V2, and V1. We could use this to get V3, which is also the voltage across these two. We could do VERC a few more times and figure out the voltages and currents. Okay, but let's do it the KVL, KCL way. And hopefully remember from your math classes, you have to have the same number of variables as you have, or same number of equations as you have variables if you want to be able to solve. So sometimes I might, on a test or whatever, ask you to just write the equations you would need to write to solve. If we have 3 equations, 3 unknowns, that's quite a bit of algebra. It might take quite a while on a test, and so I might just tell you to write the equations. And so you'll have to count how many variables you have, or define however many variables you define, you have to write that many equations. So that's another reason to go ahead and write the Ohm's law things on here, because if we do this, now we can forget about the voltages, because they're defined in terms of the currents, and we can just write equations for the currents. And so if we count up how many currents we have, basically it's how many branches do we have in the circuit. We have 3, right? We have IS, I3, and I4. And so we can write 3 equations, and we'll have the 3 unknowns, IS, I3, and I4, and we can solve. And then the voltages will just be secondary variables that we can get once we know the currents. Because notice, every voltage, if we know the currents, we got every voltage, right? So 3 unknowns will be IS, I3, I4. So that means we need 3 equations. All right, so we can do it. So let's do KVL around this loop. KVL around the left loop, we'll call it KVL left. All right, so I already just did that here, but let's do it again. So we started, pick a point to start, go which direction you want, doesn't matter, just follow the rules and you'll get the right equation, or an equation that is equivalent somehow. It may have everything the opposite sign, whatever, but it'll be the same equation. Okay, so we'll start here, and I just like to start at a lower left usually and go clockwise. I don't know, whatever you like. So starting here, we'll hit negative Vs because we came to the source, came to an element. Whenever you come to an element, you'll need a voltage, right, across it. And so we hit the negative side first, so we put a negative sign on it. Plus V2. Continue on around, we hit the plus of V3 first. And continue on around, we hit the plus of V1. Okay, so we got one equation. Let's do another one. KVL on the right. Yeah, that's good. We could do a loop all the way around if we wanted to, but let's do the one on the right. It looks good. And so we'll start here and go around. So we start here, we walk around the loop. We hit negative V3 first. So we got negative V3. Continue on, we hit the plus of V4. Whoops. Okay, hold on, I'm not doing it right. So, well, we'll do an intermediate step here. So, I'm not writing it in terms of my variables here, am I? So, yeah, okay, we'll work on this. Negative V3 plus V4, and then coming on around, we hit the plus of V5. Get back to where we started, equals 0. So, really what I should have written, if I wanted to be careful with my math, is not write V1, V2, V3, but write what they are in terms of the current. So let's rewrite it. So we get negative Vs plus V2, but V2 is 2Is. And then plus V3, which is plus 3I3. And then come through here plus V1, but it's really 1Is equals 0. So this is the equation we want to solve with. Similarly here, negative V3 is negative 3I3 plus V4 plus 4I4, and then come around here plus V5, which is 5I4 equals 0. And so I conveniently just name my voltages with the size of the resistor, but that's just, anyway, that won't normally happen, right? And so just because V4 is not always 4I4, V4 would be whatever the resistance of this resistor is, where V4 is, that would be the number that goes here. Remember, these are all resistances multiplying. These are all IRs. All right, 2 equations, 3 unknowns. We need a KCL. We could write another KVL around here, but it would probably just give us the same information and not be an independent equation. Although it might work. You could try it. But let's do KCL. We need practice with KCL. So KCL says current in equals current out. So let's do KCL at the top middle. I guess we'll call it KCL at the top. Right? Kirchhoff current law, current in equals current out. So looking at this node, we have to define what is a node. This one's pretty easy, right? Nodes just go until they hit something, right? Nodes are connecting places. Sometimes nodes can be kind of long. See, this all is one node. This is all one node, right? But the nodes where two things connect are kind of boring, right? They're not very helpful, especially if we define the current. They help us to define the current, and then we don't have to have so many currents. Three or more things connected are more interesting. So anyway, let's go with this top node here. So I'll kind of color it, maybe just make it green. So let's do with this top greenish node here. And so what's going in terms of current? IS is going in. Anything else coming in? No, IS is the only one coming in. And sometimes we might not have any going in, then we just say 0, all right, on the ends. But we have one. Coming out, we have I3 coming out and I4 coming out. All right, so we have I3 plus I4. And of course, there are other ways to do this. We could just say positive, in is positive and out is negative, and we could just have it all on one side and say equals 0. We could do that however you want to think about it, but I think it's convenient to just say in equals out. Alrighty, so now we have 3 equations, and these are all in terms of current, so we have 3 unknowns, and we are in pretty good shape. So, how can we solve this now? Because we want to go ahead and find IS, I3, and I4. The basic equations, and then we know we can get the voltages once we have those. Okay, we already know IS, so we could do this, pretend like we were starting from scratch, wrote these equations. We could go back and find our total and do all that, but we have 3 equations, we have 3 unknowns, we know algebra. So looking at our equations, this one has all 3, this one has all 3, this one just has IS and I3. This one only has 2, and this one only has 2. And so I think I like this one. Let's go ahead and solve this one to relate I3 to I4. And so I guess we'll just kind of go down here. So what do we get? We have negative 3I3, and then we've got 4I4 plus 5I4. So we get 9I4. If we bring that I3, 3I3 to the other side, we have 9I4 equals 3I3. And so that would say I3 equals 3I4, right? Divide 3 by 3. So let's just kind of save that one as a little helper equation. And now let's, which one do we want to use? This one has all of them in it, so let's use this guy over here. Let's take this one down and say that now we write that one in terms of, let's back up. Just because it was a nice number doesn't make it necessarily convenient for solving. So if we can get it in terms of I4 in terms of I3 and IS in terms of I3 and put that into here, then we can solve it for I3. It'll be the only variable. So let's do it the other way. So let's say I4 then is equal to 1/3 I3. All right, and then we'll use this one, and it'll say, what was this? This is IS. All right, so you got 3IS plus 3I3 equals VS, and so IS equals VS minus 3I3. IS equals VS. Bring that to the other side. We've got 3I3, bring that to the other side, so it's a minus, and then we've got 3IS to divide by 3. So when you do the notes, maybe do a little more algebra to prove if I'm right or wrong, but I think IS is VS minus 3I3, or IS is VS over 3 minus I3. All right, so now we've got IS in terms of I3 and other known things, and I4 in terms of I3 and other known things, so we can put them into here. And so we'll have IS, which is VS over 3 minus I3. So taking this one, going down here, equals I3 plus I4, which is 1/3 of I3. And again, however you like to do your algebra, you could, if you're into, if you've done linear algebra, you can make it into a matrix and use your calculator to solve it with matrices. It's the kind of things we would do in circuits and so forth, but we'll just go ahead and do the algebra by hand here. Looks like a lot of 1/3, so let's multiply by 3. So we'll have Vs minus 3I3 equals 3I3 plus I3. All right, I like it better. And then we will have Vs equals, this is 4, we'll have 7I3. So I3 equals Vs over 7. I hope. I'm worried. It's not right. No, that's I3. I don't know if it's right or not. So we got 12 volts over 7. So we got 12 divided by 7. 1.714 amps is I3. I hope. All right, let's check IS because we already have IS. So IS is supposed to be Vs over 3 minus I3. So 12 over 3 minus 12 sevenths. 2.286 amps equals IS. All right, so hallelujah, that's what we had before, okay? And so, and then finally I4 is 1/3 I3. So 1/3 of 12 over 7 is 4 over 7, whatever that is. 0.57. Okay, so hopefully you see, hopefully you can see. We got a system of equations, so we could do it this way, a little bit of algebra math, figure out, we found out these 3 currents. We could go, one of these is, yeah, that's an S. It looks like a 5, but that's an S. We could find any of these voltages that we wanted to now, the voltage on any resistor, calculate the power everywhere. Basically, we've got the whole circuit solved since we solved this system of equations. And again, starts from naming your V's and I's correctly with passive sign convention, writing your KVLs correctly according to what you named them, the direction the current arrows were, where the positive and negatives were on the voltages, and then you can get it. So you could have named them totally differently, but if you wrote your equations correctly, you should get the same answers that I did. All right, let's stop there.